Ready for a deep dive? We're tackling a paper that really shook things up in the world of AI.
Should be interesting.
Yeah, this one's a biggie. Attention is all you need. The paper that introduced everyone to the transformer model. Sounds a little intimidating maybe, but trust me, this paper is a game changer. And with a little, guidance, it's surprisingly understandable.
I'm all ears.
Perfect. So to really grasp its impact, we got to start with a problem that used to be a real headache in natural language processing, NLP. We're talking about sequence transduction.
Sequence transduction.
Yeah, things like translating languages or summarizing text, basically taking one sequence of words and, transforming it into another.
Right, I see. And traditionally, RNNs were used for this, right? Recurrent neural networks.
You got it. Think of them like the super dedicated note takers, processing info one step at a time.
Yeah, for a while that worked pretty well.
Until you hit them with like a crazy long sentence.
Exactly. That sequential processing, while accurate, could be slow.
Yeah.
Resource intensive.
Yeah.
RNNs start to really struggle with those longer sequences. Makes them trickier to train, too.
Yeah, it's like trying to speed read a really dense novel,
I know exactly what you mean.
It's going to take a while and you might miss some of the nuances.
For sure.
And that is where our star paper steps onto the scene. With a pretty bold statement.
Yeah.
What if we just ditch this whole recurrence thing, entirely, and just rely on attention?
Wow. That was a radical idea.
It really was.
It sent shockwaves through the field of NLP. Because this paper didn't just suggest a new model. It totally changed how we look at language understanding in AI.
Huge. So let's talk about this attention that's got everyone so fired up. What is it? How does it work in, the context of AI?
Okay, so think about how we understand language. We don't just process words one after the other in isolation.
No, not at all.
We're constantly shifting our attention.
Right.
Focusing on different parts of a sentence or a paragraph to really get the meaning.
Yeah.
And the transformer, with its attention mechanism, tries to do the same thing.
So it's like our brains are always highlighting the important stuff as we read, making connections between words and phrases and all that.
Exactly. The transformer's attention mechanism lets it focus on different parts of the input when it's generating the output, just like when we read.
Gotcha.
This means it can capture those long-range dependencies between words, the ones that might get missed by a strictly sequential model.
Okay, so it's not just about the order of words, but the relationships between them? Cool, but how does the model actually pay attention? It's not like it's got eyes scanning a page, right?
Right, and that is where the magic of, get this, scaled dot product attention comes in.
Snappy.
This specific type of attention, it was introduced in this paper, and basically it figures out how much each word should attend to every other word in the sentence.
Interesting.
Creates this weighted map of connections highlighting the important parts for each output word.
That sounds wildly complicated to actually compute.
It could be, but that's the beauty of the scaled dot product attention.
Okay.
It's designed to be incredibly efficient,
Yeah.
much faster than other attention mechanisms out there.
Yeah.
And they actually show this in the paper, direct comparisons, speed, performance advantages, all that.
I bet efficiency is a beautiful word to data scientists.
Oh, yeah.
But the paper doesn't stop there, does it? They introduce this idea of multi-head attention.
Yeah, it's like the model is juggling multiple lines of thought at the same time.
Whoa, that's intense.
It's a good way to think about it. Yeah, like a team of experts, each one specializing in, a different aspect of language, and they're all analyzing the same text at the same time.
Oh, I like that.
One might be all about the grammar, another one's picking up on the sentiment, another one's looking at how the words connect across the whole sentence.
Wow.
All happening at the same time.
So it's like having multiple perspectives on the same text. No wonder this model was such a game changer.
Absolutely. This multi-headed approach, it lets the model capture so much more, different levels of meaning, context, all at once.
And all this without a single RNN in the picture. When we look at figure 1 in the paper, the model architecture diagram, it's pretty clear the transformer is a different beast.
Totally different. Instead of those, linear chains of RNNs, we
Yeah.
see these stacks of encoder and decoder layers.
Right.
And they're both powered by, you guessed it, self-attention.
Of course. So let's break those down a bit. What are these encoder and decoder layers actually doing?
Okay, so the encoder is like the part of the model that reads and understands the input, the sequence. It processes the text, right? It's figuring out how the words relate, building this rich picture of the whole thing.
Gotcha.
And then the decoder takes that picture, that representation, and uses it to actually generate the output, word by word.
Okay, so it's like the encoder is taking notes, highlighting the key points and then handing them off to the decoder to actually write the final message.
Perfect analogy. That's
Yeah.
exactly it. And within both the encoder and decoder, you've got those self-attention layers working hard.
Right.
They're the ones allowing the model to look at all the words in a sentence at the same time, figuring out how they connect, building this like complex understanding of the meaning.
But hold on, didn't we ditch recurrence to get that efficiency?
We did.
If the model's looking at all the words at once, how does it know what order they were in? The cat sat on the mat is very different from the mat sat on the cat.
Good point. And that's where another clever trick comes in positional encoding. So even though the model can process all the words in parallel, it still needs to know the order, right? So what they did was they added these signals, positional encodings, directly into the data.
Okay, hold up. What kind of signals? Like smoke signals, Morse code.
Not quite that dramatic. These signals are actually mathematical functions, sine and cosine waves, to be precise.
Sine and cosine. Okay, back to high school math class.
Right. But basically, these functions embed information about the word's position directly into the data. Each position gets a unique pattern.
So the model isn't seeing the word order directly, it's recognizing these patterns that tell it where each word goes.
You got it. And the paper compares this to other ways of encoding positions. And it's amazing. It's just as good, but so much more elegant.
And elegant solutions usually are the best ones. Now, the paper spends a whole section explaining why self-attention is better than not just RNNs, but also CNNs, those convolutional neural networks that are huge in image processing. What makes self-attention so special?
Section 4. That's where they get into the nitty-gritty of why self-attention. It really comes down to three main advantages.
Lay 'em on me.
First up, speed. Remember how we were saying RNNs get bogged down by long sequences?
Yeah.
Self-attention, it's way faster because it can process everything in parallel. Second, parallelization. This plays right into the strengths of GPUs, the powerhouse of AI.
Right, makes sense.
And third, self-attention is incredible at handling those long-range dependencies between words. Like it can connect a pronoun back to the noun it refers to, even if there's a whole bunch of other words in between.
Like, it's got this super memory for context.
Exactly.
But enough about the technical stuff. How did it actually perform? Did this crazy new architecture deliver?
Oh, it delivered big time. Table 2 in the paper is basically a victory dance.
Okay.
Showcasing the Transformer's dominance on this classic translation task, WMT 2014, English to German specifically.
And what were the results? Spill it.
The Transformer crushed all the previous records. It achieved a BLEU score. You know, that's how we measure the quality of machine translation.
Sure, higher is better.
Exactly. It got a 28.4. Previous models, the best they could do was barely break 27.
Wow, 28.4 is huge then.
It was a massive deal. And get this, it did it in just 3.5 days of training on 8 GPUs.
That's crazy fast. But they didn't stop at German, right?
No way. They also tested it on the English to French dataset. Even bigger, by the way. And guess what? Crushed it again. BLEU score of 41.0. Another state-of-the-art result. And they did it using way less computing power than those other top models.
Faster, better, cheaper, the dream. But the real test for any model is, can it do more than just one thing? Can it generalize?
And that is what makes the Transformer so remarkable. It's not a one-trick pony at all. The paper also looked at how it does with English constituency parsing, basically analyzing the grammatical structure of a sentence.
Like diagramming sentences, finding the subject, the verb, all that jazz.
You got it. And even without any special tweaks for this task, the Transformer held its own against those specialized parsing models. What's even more wild is that it did this with less training data.
So we're talking about a model that can translate languages, break down grammatical structure, could probably write a poem if you asked it to.
We haven't tested that yet. But the point is, this paper wasn't just about, hey, look at this new model.
Yeah.
It was a fundamental shift in how we approach NLP. And those amazing results, just the beginning.
What do you mean? There's more.
Way more. Those results, as incredible as they were just the tip of the iceberg. This paper, it really shook things up in the NLP world.
Yeah, it was a total paradigm shift.
Right. Suddenly we had this model that could beat everything else out there, often with less training data even. It was like, boom, the floodgates open for research into even bigger, more powerful attention-based models.
And that leads us to those large language models we see everywhere today.
Exactly. The Transformer's ability to handle those crazy long sequences, process everything in parallel, generalize to new tasks. It's what made it the perfect building block for those massive, multi-talented language models.
It's really wild to think about the impact of this one paper. It's like, discovering a new element in chemistry.
Totally.
Suddenly, this whole world of possibilities just opens up.
And speaking of new possibilities, we haven't even talked about one of the coolest parts of the paper, the attention visualizations, figures 3, 4, and 5.
No, yeah. The ones that are like peering right into the brain of the model.
Exactly. They give us this little glimpse into how the model is thinking, how it's understanding, showing us how those different attention heads are focusing on different parts of the input.
So what can we actually see in these visualizations? Give me an example.
Well, you can see how one attention head might be focusing on the grammar, the relationships between the words,
Okay.
while another one is zeroed in on those long-range dependencies, like connecting a pronoun back to whatever it's referring to, even if they're like a whole phrase apart.
So we can actually see the model making those connections that give language its meaning.
It's pretty amazing. It's almost like you can see it learning to understand language, kind
Yeah.
of mirroring how our own brains do it.
That's what makes this paper so important. It's not just that it works, it's that it gives us this window into how language understanding actually works. So as we wrap up this deep dive, here's something to think about. If these visualizations can show us how the transformer learns, what about the future? What will future versions of this model be able to do? How will they change how we think about language? How will they change how we think about intelligence itself? Keep those questions in mind, and until next time, happy diving.